All right, finishing out this lecture with my final example. Let's take a look. A girl on a sled at rest slides from the top to the bottom of a hill. Okay, so sometimes it's helpful to have a picture. So here's our hill. And she's on a sled. She's sliding from the top to the bottom down here. Okay, so it's always helpful to define the initial and the final moments. So I'm going to define the initial moment as up at the top and the final moment as down at the bottom here. All right, in the initial moment, it says that she is on a sled at rest. So I'm going to say that she's at rest and that she is up high, right? She's at the top of the hill. And then in the final moment down here, she is now in motion because she's just slid down, gained speed, but she's at the bottom. Okay, being a little bit more specific about what those mean for her energies. Well, if she's at rest, her kinetic energy is 0. But if she's at the top of the hill, she's going to have some sort of height here, right? So she is going to have some potential energy due to that height. And I'll just write it over here as a reminder. So kinetic energy is 1/2 mv squared. Potential energy is mass times gravity times height. I'm talking about gravitational potential energy. Okay, so kinetic energy is largely dependent on velocity. Potential energy is largely dependent on height. Okay, let's take a look at the final state. Down here at the bottom, the girl is in motion, so she has kinetic energy, some positive value of kinetic energy, but she's at the bottom and she has no height, therefore her potential energy is 0. Okay, so taking these descriptions of her initial state, putting them in here, taking these descriptions of her final state, putting them in here, and then if there's any difference, I can make that up in the work column. All right, so initially her kinetic energy is 0, so I'm going to just throw a line there indicating 0, but she has some positive value of potential energy. I'm going to say 4 bars. Okay, it's arbitrary, just some positive value. And then her final state is that she has some positive value of kinetic energy. And I'm going to say maybe 2 bars, but her potential energy is 0. Now, let's think about this for a second. In this situation, if she's sliding from the top of the hill to the bottom of the hill, it's always useful to identify whether there is friction or air resistance happening. And this problem is not clear, okay? So since it doesn't specify if there's friction from the snow or whatever, or if we should consider air resistance, I'm going to assume no friction or air resistance. Okay, and if there's no friction or air resistance, then there would be no negative work done. Okay, so I've got a problem here, which is that I have 4 bars on the left side, and I have 2 bars on the right side. Okay, and if there's no negative work done, then there's really no opportunity for energy to be lost. So then I could reason that I haven't balanced this correctly, that this 2 bars really should be 4 bars. And so I'm just going to increase that up here and balance it out. Starting with 4 bars, ending with 4 bars, there's no negative work because there's no friction or air resistance. And then, is there any positive work being done? Well, you might say that there is a force pushing this girl, which is the force of gravity, and you might wonder if gravity is doing positive work on the girl in this situation. And this is where we have to be careful. So if we were to add some sort of positive work, then the girl would magically gain more energy than she started with. I would have to add a bar over here to balance them, and then we'd have 5 bars and 5 bars. Okay. Now, what would be adding energy to the situation? You might say, well, maybe it's gravity, but here's where we have to be careful, is gravity is already being included. And I'm using this example to show you that gravity is always included here in the potential energy. Right? Potential energy is mass times gravity times height. Okay, so the work that's being done by gravity is already included in this potential energy. That's why the girl has energy up here at the top of the hill in the first place, because something pushed her up there. She climbed up there herself. So she's already gained energy because of gravity at the top, and we don't need to add it again in the center column. Okay, so here is my note to you, is that when you're thinking of work, I'm going to try to clear some space here. When you're thinking of work, I'm going to say always exclude gravity. Okay? It's already baked into the potential energy that you're seeing here. All right, so this is it. This is an example of when no work is done by some sort of outside force, and the girl experiences a perfect transformation of all of her energy from one type to another. So her energy is perfectly converted from gravitational potential to kinetic energy.